Good morning. I'm Alejandro Soto,
I'm Walter Fon.
and today we're going to talk about the Nebulae, our 64-bit processor, which we engineered for CACS 440.
Alright, Alex, so what's on the agenda for today?
So for the agenda for today, we're going to talk about the history of the 64-bit processor, about us, the future enhancements we're going to use, and why we named our processor what we did, the design details, the enhancements that we've made to our 64-bit processor, some examples of our enhancements, design blocks, which is all the architecture behind it, and in the end we're going to have time for you to ask us questions. So history about the Nebulae. The reason we gave it that name was because we wanted something out of this world, and nebulae are, something out of this world. And the future enhancements we wanted to add were also out of this world, so we thought it was a perfect name for it.
Alright. So going into the design details. So to start off, our instruction sets, like everyone else here, they had single operands, double operands, triple operands. We had conditional and unconditional jumps, immediate instructions, floating point instructions. For our addressing modes, we have the registers, barrel shifters, immediate, and register indirect modes. And talk a little bit about memory. We have a Harvard architect risk design. So in there, all of these registers here are almost all in the VIU. So we have the 32-bit stack pointer, 32-bit memory address. Both of those point into the data memory. We have the 32-bit instruction pointer, 32-bit instruction register, and we have 32-bit floating registers and 32-bit integer registers, each 64-bit flag. And for our flags, we have the negative, the carry, the zero, the overflow, and the interrupt enable. All of those are 1-bit wide. And our format is Little Endian format. So as you can see from this picture, top 63 to 32 go first. Then we have the reverse. 31 to 0 go first, and then the 62 to 32. Alex is going to continue off more about the.
So we have 80 total instructions, 4 enhanced, which are barrel shifter instructions. As we said, we have a RISC type architecture, so its loads and stores are the only things that could access memory. And we have multiple clock cycles per instruction. We have a floating point specific ALU, as well as for the integer data path. So I'm going to talk about our enhancements. So we have barrel shift left. So we have a pretty unique way of using the barrel shift. We actually get the shift amount from IR 8 to 15. So we had to develop a new addressing mode. So 8 to 15 is a 6 bits, which would allow us to shift up to 64 times. That shift amount would go into the ALU, and it would perform an algorithm that we developed, which I'm going to explain in the next page. But this is how barrel shift left occurs. I used 8 bits to simplify it for you guys, because 64 bits would probably take this whole page. But here's a quick example for 8 bits. So you would have a copy, so it's 8 bits on the left, 8 bits on the right. On your left, you would get that value that you're trying to shift, and on the right, you'll set everything to 0. Then in the left, you do a 7 minus the shift amount, which it would be whatever SA was the shift amount. And in the end, you would just do a concatenation, and you'll receive the result. In the next page, I'm going to give you an example. And this is barrel shift right, which would work the same way, except it would be the opposite of barrel shift left. And also, we have a barrel rotate, which would work similar to, but different as well. Because logical shift left, we shift in 0 bits, while rotate right, you don't shift in anything. You keep using the bits that are in that value. But we would also use shift amount, which would come from IR 8 to 15, and would also go into our AOU to perform the operation. So we had to add that into our AOU. So an example of the barrel shift. So barrel shift left. So I made it simple, so I made 8 bits. So what would happen is you would get a 100111010. So that would be copied into your left. So that's your R, left is equal to R. And then you left those 8 bits on your right side be 0. And then you'll perform this operation right here, which it's an algorithm, which I figured out using 4 bits that would always work every single time. So it would be 7 minus the shift amount, which would be 4. 7 minus 3 is 4. And then it would be 4 to 0. And you would do the same thing for your right, so it would be 7 to 7 minus SA shift amount, which you would end up with 7 to 3. So what you do is you'd get the 0 to 4 of the left, 0 to 4 of the left, and then 7 to 3 of your right, and that would be your result. And it would work the same way for. Go back. So that's for your barrel shift left. Barrel shift right is the same way, except you would shift around the bits. And here's an example for your barrel roll to your right. Very similar to the barrel shift left, but it's a little bit different. And here's how I'm going to explain it a little bit. So I use 8 bits as well. So this is the value that I'm trying to rotate. So I copy that into my left, and then I copy that to my right. And then I perform the operation to see what bits I'm going to need. So so when I do this with this algorithm, I come up with y is equal to left 0 to 4, and right is equal to 5 to 7. And if I get those bits, I end up with this result. And so that that's way quicker than that, and that always works every single time.
While we're here, you said you developed it using a 4-bit thing?
I looked at it like doing 4 bits,
Yeah.
and I just figured that out. That always worked every single time.
That's awesome. Good job.
I'm going to talk about our block designs. So this is our top level block. We have our control unit here on the left, our execution unit, the memories, and an I/O module. Now, our I/O module, we treated it as an extra memory module for this simulation. But as you can see, most of the control signals flow from, well, in this case, from left to right, all of them going into the execution unit, and from the execution unit, flow to the memory of the data memory, instruction memory, or the I/O. Now, things that are coming back are, for example, like the flags and the interrupts going into the control unit. And also, for simplicity, we didn't include a clock and a reset on this design, because all of them have clocks and resets here. And so all our control signals coming from the control unit, our finite state machine, that includes the 80 plus 4 instructions inside. So now we're going to go take a deeper look into the execution unit, as the control unit is just that. So, apologize for the colors, I'm not very good with color matching, but so we have our bus interface unit, the integer data path, and the floating point data path. Everything basically going into the bus interface unit and then into the data paths above. Like we said before, we have 32 integer data path registers and 32 floating point data path registers, all of them 64-bit wide. And we have controls addresses over here and over there that basically direct which addresses we're going to be using for the particular operations. We also have different select methods to basically allow for a value coming straight into memory to go straight into the data path registers. That's our Y select and FY select. And now going more into the bus interface unit, since we have 2 different memories, we have 2 different buses. We have the iData bus and the instruction data bus and the data memory bus. And then for the data bus, we have the address selection from the MUX, where we select either the MAR or the SP. And the SV is our stack pointer, which basically starts off at the basic end of the memory at pre-FE. And then with our push and pops instructions, either decrements or increments. And then for our read buff, we have muxes there that either take the data from the instruction memory or the data memory. Our floating point just basically goes straight into the data memory. However, they all have output enable signals since our data buses are only 32 bits wide, so we have to control the flow of it in little endian format. And into our IP, as you can see, we have a mux right before it that feeds into it. And for our jumps, for example, we have called it design extension logic, where we also have our adder that goes into the IP that then selects the next instruction address that we have to jump to. And now we also have, for the stack pointer, different muxes as well, depending on the instructions that is being operated. And now going into the integer data path, nothing much has changed here. Our barrel shifter is actually inside our ALU, so it's not going to show over here. And for our floating point, it's still the same, nothing else has changed. And for our future enhancements, we're looking to add a divide by 0. Now this is a pretty easy task to put, but we just didn't put it because we didn't want to break something at the end of when we got it to work. And also we want to add a vector data path. Alex is going to talk more about that as well.
Well, just how we have an integer data path to subtract, add, multiply, divide integers, we wanted to do the same for vectors. So we wanted to implement that in the future for our Nebula 64-bit processor.
Now, those are basically the enhancements that we wanted to add. And any questions?
So I have a question. When you say divide by 0, do you mean like an interrupt?
Just check for the 0. So when we're dividing by 0, we get an undefined.
Okay.
That's basically what we wanted to add. Further questions?
So then what is it currently doing?
Just executes the instruction, really. Yeah, it doesn't do anything. It doesn't catch the undefined error.
Will it just be, if compare with 0, and then if it's 0, don't do
exactly.
the whole algorithm division that we have? Okay.
It's pretty simple.
It's a pretty simple addition.
We actually incorporated it, but it was after we had already turned it in.
Okay.
We just didn't want to break anything.
So it makes no sense.
Any others?
Good, thank you very much.